So we will be continuing with the bit manipulation playlist. Before that, hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So in this video, I'll be covering up a lot of problems. Yes, and the first problem will be swap two numbers. So the problem statement is swap two numbers. So you'll be given two numbers, A and B. So assume A is given as 5, B is given as 6. Now your task is to swap them. So after swapping, A will be having 6, B will be having 5. How can I do it? It's very simple. I can say, I'll take a third variable temp. I'll store the value of A into it. So temporary will be having the value 5 initially when we start with this state. Done. After that I say, okay, A equal to B. So I take the value of B, which is 6, and I put it into A. After that I say B equal to, can I say B equal to A? I cannot. Why? Because if I say B equal to A, A's value is 6. So B will still stay as 6. This is the reason I took a third variable temporary. So basically I'll say B equal to temp. B will be taking the value 5. So it'll be 5. Done and dusted. But over here, I'm using a third variable. Now in an interview, the interviewer might ask you, can you solve this without using the third variable? Now that is where the XOR operator will come in. Now what is the XOR operator? Quick recap. Even number of ones will be 0. Odd number of ones will be 1. Can I say that if I XOR two same numbers, 5 XOR 5, the value will be 0. Why? Because 5 is 1, 0, 1 in binary, and again 5 is 1, 0, 1 in binary. If I'm doing a XOR, since they are same numbers, every row will have even number of ones, and wherever there is 0, there will be even number of ones, that is 0 number of ones. So everything will be 0, 0, 0. So thereby XOR of same numbers will be 0. So I will be using the XOR operator in order to swap two numbers. Let us see how. So what I'll write is A equal to A XOR B, and this will be my step number 1. After this I'll write B equal to A XOR B again, right? So if I write this, what will happen is this A, what is the value of this A? Can I say this much? It is, because this is what I did in step 1. So I can write A XOR B is what A is, and then a XOR of B. Now what is B XOR B? That is 0. So eventually B is equal to A. Agreed or not? Agreed. After this I'll again write A equal to A XOR B. Now tell me one thing. What is the value of A? The value of A is this much. Right? So I'll write this again. A XOR B, XOR of B. This time what is the value of B? It's A. It is A, right? So I can just write it as A. It is not B anymore. It is A. So A XOR A will go off as 0, and eventually you will be left out with B. So if you see, what we did was B equal to A equal to B. The XOR operation will do it for you. So this is how you can easily swap. So it's very simple. 3 lines, and you can easily swap two numbers without using the third variable. So time for the next problem, which is check if the ith bit is set or not. So what is the problem stating? It's stating that you'll be given a value n, imagine 13, and you'll be given a value I, imagine 2. Now your task is to check if the second bit in the number 13 is set or not. So what is 13 in binary? 1, 1, 0, 1. Agreed? This is what 13 is in binary. Now your task is to check if the second bit, and you count the bits from the right to left. So 0, first, second. Is the second bit set? It'll be like, yes, it is set. So I'll have to return a true. Got it? Imagine I change the value. I change this to, let's say 1. In that case, this is the 0th bit. This is the first bit, and it is not set. So it'll be returning false. I can probably ask you 10th bit as well. If I ask you if the 10th bit is set or not, in that case, you'll have hypothetical zeros, so it will never be set. Got it? So how do you solve this problem? The brute force that I can think of is, I take the number 13, convert it into its binary equivalent. We have already done it. After that, I start traversing from the back, and I figure out if the ith bit is 1 or 0. And then I can return a true or false. But for that, I'll have to convert a number into its binary. I don't want to do it. How can I do it with using bitwise operators? So there are two ways. One is the left shift operator, while the other one is the right shift operator. I've already done, I've already told you about this in the last video, right? So let's understand how can I use the left shift operator. So if I write 13, that's 1101 technically in binary, right? I've been asked for I equal to 2, which is the second bit. So where is the second bit? Here. So can I write something like 1 left shift of 2, which is basically I. 1 left shift of I. So what will happen is, if I write this is 1. So on shifting it by 1 place to the left, you'll get something as 1 here and then a 0. And if you try to again shift it, you'll get 1, 0, 0. So this is the number that you'll get if you try to shift 1 by 2 places. Got it? So what you'll do is, you will take 1 left shift of I places. So what you'll get is 1, 0, 0. Once you have this, what you can do is, you can simply do the AND operation. So if you do an AND operation, you know one thing for sure. Apart from this 1, everything else is a 0. Apart from this 1, everything else is a 0. So if you're doing an AND, all of these places will be 0 for sure, because you have a 0, and if you do an AND with 0, you get a 0. But for this one, if this is 1, you will end up writing 1. If this is 0, you'll end up writing 0, right? So you will basically get a number which is greater than 0, right? So I can say one thing, okay, if n and 1 left shift of I, if this is a non-zero number, I'm very sure it is set, else it is unset. Super simple. Let me take an example where it is unset. So if I take the number 13, we will use some other color, n equal to 13 and I equal to 1. What will happen in this case is, 13 is 1, 1, 0, 1, correct? I is 1, so I'm saying 1 left shift of 1 place, that is basically here. And then there is a 0, so everything else is 0. So everyone else will go 0, and this is a 0, so thereby this will also go 0. So you'll eventually get 0. Got it? So if you say n and 1 left shift of I is the number, like the bit that you want to check. And if that is non-zero, that means it is set, otherwise it is unset. So this is how you can easily do it by using the left shift operator. So let's now understand how can I do it by using the right shift operator. So what is 13? 1, 1, 0, 1. I have to check the second bit. That's basically 0, 1, 2. This is the bit that I want to check. So what I will do is, I'll try to take this bit to the extreme right. I'll try to take this bit to the extreme right. So I'll say right shift by 2 places. Right shift by 2 places. So what will happen is, this 0 and this 1 will go off the cliff. And this 1 will be here. This 1 will be here and everything else will be 0. After shifting it right by 2 places. Done. So this is the bit that you want to check if it is set or not. So what you will do is, you'll do an AND with 1. You'll do an AND with 1. So if this is set, it will automatically give you 1 and all the other things will be 0. So they will be 0. So if this number is 1, if this number is, because this is 1, in decimal this is 1. If this number is 1, it is set, otherwise it is unset. Let me take one more example. Imagine if n is 13 and I is 1. In this case, 13 is 1, 1, 0, 1. I have to shift it right by 1 place. That means this will go off the cliff. This 0 will be here, this 1 will be here, this 1 will be here, and everything else will be 0. Now what you do is, AND with 1. So if you do an AND with 1, everything else is 0. So 0, 0, 0. And this will also be 0. So what you basically write is, if n right shift by I places with an AND of 1, if that is equal to 0, that means it is unset, else it is set. So either you right shift and bring this one to the extreme right. Either you can do that, or you can left shift and place a 1 right below that bit. Simple. By left shift or by right shift. So the time complexity and the space complexity will be big of 1. It is extremely fast because the computer performs bitwise operations much faster than all the other operations. So the next problem is setting the ith bit. So the problem is stating that it will be given a value of n, imagine 9. It will be given a value of I, imagine 2. So if I try to write 9 in its binary, it will be 1, 0, 0, 1. Now the second bit from the right is 0, 1, 2. This is 0. Your task is to set it to 1. Your task is to set the ith bit to 1 and keep all the other bits as it is. Once you have done it, the value will be 13. Now what if this was 1? You still keep it as 1. Doesn't matter. You have to make that bit as 1. So the number is 13. Now what if I ask you the brute force? The brute force is very simple. You convert it into its binary, which is 1, 0, 0, 1. You figure out the second bit. You make it 1 and then you convert it back into its decimal. A long process. Can I do it in a better way? Probably yes. Let's try to write 9 in its binary. 1, 0, 0, 1. I'm trying to convert this bit, which is the second bit. So what if I can place a 1 over here? Can I place a 1 right underneath it? Probably I can. What I'll try to do is I'll take a 1, which is technically something like 0, 0, 0, 0, 0, 0, like dot, 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 32 bits. That's 1. If I say left shift by 2 places, this number will be, so this 1 will go here, left shift, and this will be 0. You know the left shift operator, right? This is what you will get. Something like this, right? Agreed? After this, if you try to do a OR operation, so this is 1. If you do OR with 0 or 1, doesn't matter. It will always be 1. This is 0, and you're sure that the underneath value is 0 as well. So this will always be 0. Now this is 0, but the underneath value is 1 because you have done it. That's why this will be 1, because you're doing a OR operator. After that, this is 1, so it will just be 1. So apart from this, whatever the bits were, they will basically get transferred. And this 0 will turn into 1 because you're doing an OR with 1. Got it? So this is how I can do it. Quite simple. I'll write n OR, which is the pipe operator, and 1 left shift of I. This is how I can set the ith bit. Got it? Even if it is 1, let's take that example as well. So if I take n equal to 13, I ask you to set the second bit again. So what is 13? That's 1, 1, 0, 1. Now this is the second bit, right? I'll try to place a 1 here, which is basically 1 left shift of 2 places. So I'll get something like this. And then I do a OR. What will happen? 1, 0, 1 or 1. That's 1. 1 or 0. That's 1. So you'll still get the same number. If it is set, you'll get the same number. If it is not set, in that case, what you'll get is, in this case, you got the number, right? So this is how you can easily set the ith bit using the bitwise operator. So the next question is clearing the ith bit. Now the problem states it will be given a value n. Let's take 13. It will be given I. Let's take 2. Now your task is to, basically 13 in binary is 1, 1, 0, 1. Now your task is to clear the ith bit, which is 0, 1, 2. Your task is to clear the second bit. Clearing means turn the 1 to 0. And if it is 0, keep it as 0. So if you clear this, this will turn to 0 and the rest will stay as it is. So the number will be 9. Again, the brute force will be convert this into its binary. Once you've done it, go to the second bit, put a 0, and again reconvert it into its decimal. That is a long process. So what will be the brute force? What will be the process using bitwise operators? It's going to be very simple. What is 13? 1, 1, 0, 1, right? I want to turn it off. So can I say, if I put a 0 here, and I put 1 across all the numbers, all the 32 bits, I put a 1. And after that, if I do an AND, will it work? It will. Because if I put a AND, because of the 0, this will turn out to be 0. And all the other numbers, if this is 1 and there's a 1, so AND will give you 1. And if this is a 0 AND with anything will give you a 0. Agreed? 0 AND with anything will give you a 0. Again, 1 will always be AND with a 1. So 1. Again, 0, 0. So you will actually turn it off. The only thing that you need to do is, you need to somehow make sure that this ith bit is 0 and your job will be done. Again, it is very, very simple. Just think how can you do it. I'll give you a hint. First step is, try to place a 1 over here and rest all zeros. Can you do that? Probably yes, we can do that. How can I do that? It's going to be very simple. I say 1, left shift of I, which is 2. So I'll get this value something like 1, 0, 0 and all zeros, because 1 left shift by 2 places will put the 1 over here, right? I'll do a negation of it. I'll do a NOT operator of it. So once I put the NOT operator, what will happen is, this was something like 0, 1, 0, 0. I'm not writing all the 32 bits. I'll do a NOT of it. So this will turn out to be 1, 0, 1, 1 and rest all are ones. So basically 1, 1, 0, 1, 1, 1 and all are ones. And you do an AND with it. So 1 and 1 is 1, 0 and 1 is 0, 1 and 0 will turn it off. 1, 0, 0. So you basically turn off that bit. So how you can do it is N and negation of 1, left shift of I. Very, very simple. That understood. So the next question is toggling the ith bit. Now the problem is stating that you'll be given a value n. Again, let's take 13 and let's take I equal to 2. So basically 13 in its binary is 1, 1, 0, 1, which is the second bit. That is 1. You'll have to toggle it, change it. So this will become 0. This will be 1. This will be 0. This will be 1. So that's 9. Now I'm asking you to toggle, not clear. Toggling is different. Imagine I give you n equal to 13, I equal to 1. So in this case, 1, 1, 0, 1. First bit is this one. So after toggling, it'll be 1, 1, 1, 1. So you make a 0 to 1 and you make a 1 to 0. Reverse it. Whatever is the bit at the ith position or index, whatever you can call it. How can I do it? It's, again, very simple. Hint is XOR operator. Like, again, the brute force is take this number, convert it into its binary equivalent, which is 1, 1, 0, 1. Figure out the second bit. If it is 1, make it 0 or vice versa and convert it into its decimal. But how can you do it with using bitwise operator? The hint is XOR. You can try it out. So what you will do is, you'll take the number 1, 1, 0, 1 and write it in its binary. Written. After that, you try to think, okay, this is the bit that I'm looking forward to change. If I'm able to put a 1 underneath it, again, it's very simple. You know how to do it. 1 left shift of I. If I do this, I will be able to put a 1 underneath it. Okay. And all the other things are 0. Now, can I say if I do a XOR, what will happen is Ones or 1, because it is even number of ones, will turn out to be 0. It will toggle it. And the rest, ones or 0. 1, odd number of ones, so 1. Zeros or 0 is 0. Ones or 0 is 1. Right? So you actually toggled it and you kept all the bits same. Will it work for the other case, which is if it is unset? Let's take the example. N equal to 13, I equal to 1. Let's try to write it. 1, 1, 0, 1. I'm trying to toggle this. So I'll again put a 1 over here, which is 1, left shift up 1, right? And put a 0 at all the other places. I'll try doing a XOR. So 1 XOR 0, again odd number of ones, so 1s. 0 XOR 1, again odd number of 1, so 1. 1 XOR 0, 1. 1 XOR 0, 1. So you actually toggled the 0 to a 1. You actually toggled this 1 to a 0. You're able to do it. Super simple. You say N XOR 1 left shift of I. That's it. That is how you can easily toggle the ith bit. So time for the next problem, which is removing the last set bit. So in this problem, you'll be given a value n. And your task is to remove the last set bit or the rightmost set bit. So if I try to write 12 in binary, it will be 1, 1, 0, 0. And if I ask you which is the last set bit, can I say the rightmost set bit is this one? Yes. I have to turn this, like remove it or just clear it. So after clearing, it will be 0 and the rest will be 0. So this is what you will get. So if I ask you for 13, if I have to remove the last set bit, it will be 1, 1, 0, 1. So the last set bit is this one. So you'll get it as 1, 1, 0, 0. Got it? If I give you a value as 16, that is 1, 0, 0, 0, another 0. Now, which one is the last set bit? This one. So the number will be 0, 0, 0, 0, which is technically 0. How can you remove the last set bit? Again, if I have to do the brute force way, it's super simple. Convert this into its binary, traverse and check the last set bit, make it 0, and again convert it back into its decimal equivalent. But obviously, we don't want to do it like that. So we'll think of a bitwise operation that will help us to do it. So before I move on to the solution, which will be a one-liner, let us observe something. So n is 16, right? That's basically 1, 0, 0, 0, and probably one more 0, yeah. This is 16. If I say n 15, which is basically n minus 1, if I take 15, that will be 0, 1, 1, 1, 1. This is 15. Okay. So n is 40. If I try to write it, it will be 32 plus 8. So 32, the 16 will go as 0 and then there's 8. So this is 8 and then this one. I think, yeah, this is 40. So this is 40, right? If I take the number 39, I can actually write 39 without thinking, and that will be 1, 0, 0, 1, 1, 1. Yes, this is 39 for sure. So let's write the binary for 84. It will be 1, 0, 1, 0, 1, 00. So this is for 84. If I ask you to write for 83, it will be 1, 0, 1, 0, a 0, and then a 1, 1. Time to observe something. The rightmost set bit is this one. The moment you do n minus 1, the rightmost set bit is converted to 0 and all the right bits that were there, because all of them will be 0. Because I'm talking about rightmost set bit. So everything to the right will be zeros. All of them will get converted into 1. Yes. Again, let's try to observe. So this is the rightmost set bit. I'm converting n to n minus 1. What will happen is 1, 0 is 1, 0. This one gets converted into 0. And all the zeros to the right will get converted into 1. Okay, works. Let's look at 84. So when I take 84, this is the rightmost bit. So I'll reduce 84 by 1. What will happen is 1, 0, 1, 0. And this one gets converted into 0. And the rightmost zeros will be 1 and 1. Yes, this is what happens. Why does it happen? Let's understand that. So I'm saying 16. Now what was 16? 16 was nothing but 2 to the power 4, right? 2 to the power 4 was 16. 15 will be all the powers of 2 lesser than it, which is basically 8 plus 4 plus 2 plus 1. Because this was straight away 16. Okay. Let's look at 40. What was 40? 40 was 32 plus 8, which is basically 2 to the power 5 plus 2 to the power 3. Right? So what happens is 32 stays, and when you convert it into 39, which is 1 reduction. So this 8 goes to the nearest number down, which is 7. And 7, is 4 plus 2 plus 1. Because of this 4 plus 2 plus 1, all of them are set as 1. Got it? I hope you have understood what happens. So the observation that we will draw from here is the rightmost bit is turned to 0 and everything else on the right is turned to 1, 1, 1, 1. If you take a number down. Remember this. So I've been asked to remove the last set bit. How can I do it? It is super simple. All you need to write is, I'll probably erase this. Yeah. All you need to do is, you'll have to write n and n minus 1. Why does it work? Let's take 40. So what is 40? That's 1, 0, 1, 0, 0, 0. Which is the rightmost set bit? You'll have to remove it. So you take an AND, right? Remember, you need to remove this only. So you'll just turn it to 0 and everything else stays as 0, and you copy paste this on the left, whatever it is, you just copy paste as it is. So what you need to do is, if you take n minus 1, which is basically 1, 0, this will be 0 and all the other things will be 1. So what happens is, if you're doing an AND, this 1 and 0 will be 0, everything else will be 0. And since you're taking the same numbers, because on the left, there is no change. So if you do an AND, you exactly get the same numbers. Got it? Let's take one more example. Let's take n as, 84. So if I take n as 84, that's basically 1, 0, 1, 0, 1, 00, right? Again, what do I need to do? I need to turn off this bit. So which is basically, I'll have to make a 0 here, 0, and everything else on the left stays as it is. So again, the same thing. If I take, this is n, if I take n minus 1, which is, this is 0, this is 1, this is 1, and everything else stays as it is. If I do an AND, the 0, 1 will be 0, 0, 1 will be 0, and this 1 and 0 will be 0. And since these are same, they stay the same. So if you do n and n minus 1, that will be removing the last set bit. So time for the next question, that is checking if the number is a power of 2 or not. So the problem statement will be giving you a number n. Imagine it is 16. Is it a power of 2? Yes, it is 2 to the power 4. Imagine you're given a number n equal to 13. Is it a power of 2? No, it is not. Imagine you're given a number n equal to 32. Is it a power of 2? Yes, it is. How can you say this? Now, the easiest, like the brute force, is very simple. You take 16, convert it into its binary. Done. Once you have converted it into its binary, you check the number of ones. So you just get 1, right? 1 set bit. So you can say that, okay, there is 1 set bit. So yes, it is a power of 2. If you take 13, convert it into its binary, which is 1, 1, 0, 1. How many set bits? 3 set bits. So this is not a power of 2. If you again look at 32, how many set bits? 1, 0, 0, 0, 0, 0. I think that is, probably that is 32. Again, 1 set bit. So technically I know one thing. There must be 1 set bit. But I cannot do the brute force where I convert this into its binary and then figure it out. So can I have a different way? Probably yes. I know that every power of 2 will have 1 set bit in it. 1 set bit in it. So can I do this? N and n minus 1. If this is equivalent to 0, it's a power of 2 or else it is not. Yes, I've already told you what happens when you do n minus 1. So if 16 is 1, 0, 0, 0, 0, if you do n minus 1, the rightmost bit, that is turned off, and everything on the right is turned into 1. Now since for power of 2's, there's only one set bit, there'll be nothing on the left. So when you do an AND, everything turns out to be 0. Everything turns out to be 0. Got it? In the same case, when you take 13, what happens is, 13 is 1, 1, 0, 1, right? So when I say 12, that's nothing but 1, 1, 0, 0, because I'm taking n and n minus 1, and I'm doing an AND with it. So what happens is, when you do an AND, this is 0, but because of the left bits, to the rightmost set bit, there are left bits, there are numbers formed. So this will never be 0, So can I say this, that if I write n and n minus 1, because every power of 2 only has one set bit, and if I'm turning it off, everything will be 0. So this is how you can easily check if a number is a power of 2 using bitwise operator, one-liner. So time for the next problem, that is counting the number of set bits in a given number. So imagine you're given a number 16. So you'll have to write it in its binary. So that will be 1, 0, 0, 0. How many number of set bits? Only 1. So it'll return me 1. Imagine again you're given 13. So what will it be in its binary? 1, 1, 0, 1. 1, 2, 3. So you'll return me 3. Got it? How can I do it? Is there a one-liner? Now there is no one-liner. It will be pure brute force. So let us write the brute force. What I'll do is, I'll have to count. So I'll take counter equal to 0. I'll start with the number 13. So in order to convert a decimal to its binary, I divide by 2. So when I divide by 2, I get a remainder 1. So I'll just increase the counter by 1. Perfect. So there is 6. Again divide by 2. So this time the remainder is 0. So I'll not increase the counter. Again divide by 2. This time the remainder is 1. So please increase the counter by 1. Again divide by 2, so you'll get 1. So when you get 1, you stop then and there. So when you stop, at the end you had 1. So you will increase the counter by 1. Simple as that. So can I write down the function? Probably yes. I'll say integer count set bits. And I can take the number int n. Perfect. What is the first thing that I'll do? I'll take a variable counter. And then I know I'll have to write a while loop. While n greater than 1. Right? Because that is when we stop. So can I say, if n modulo 2 equal to 0, if n modulo 2 equal to 0, I don't count anything because the remainder is not there. So can I write, if the remainder is 1, then I say counter plus equal to 1. Can I say this? I can. And after this I can say n equal to n divided by 2. Done and dusted. At the end of the day, if the n is equal to 1, you increase the counter by 1 and then you return that. Done. Looks okay, right? But can I do something else? Probably yes. Now this is checking for odd. Right. If there is a remainder, it means it is checking for odd. So can I write something as n and 1 instead of writing n modulo 2? Can I write n and 1? Probably yes. Now let's take an odd number. 13 for that reason is an odd number. So 1, 1, 0, 1. So if I do AND with 1, I'll get 1 and rest of all of them will be zeros. Right? Why did I get a 1? Because the last bit of an odd number will always be 1. The last bit of an odd number will always be 1. Let's take for that reason 6. So if I try to write 6, that will be 4 plus 2, right? 1, 1, 0. Yeah, that is 6. last bit is not set. So if I do an AND with 1, I'll get 0, 0, 0. Why is the last bit set? Because if I'll have to write 13, 13 is 8 plus 4 plus 1. Only the last bit will give you 1. Only the last bit will give you 1. Apart from that, all of them will be even numbers. Even plus even will be even. And then if you add an odd number which is 1, you actually get 13. For 6, it is 4 plus 2. For 7, it is 4 plus 2 plus 1. For every odd number, you'll have to add a 1. So the last bit for all the odd numbers will always be set. Will always be set. Remember this. So if it is set, can I replace this by if n and 1? I can. Or can I say counter plus equal to n and 1? Because this will return 1 if it is odd and this will return 0 if it is even. Bitwise. And what about this? You know it. Which operator? Yes, right shift. So can I write n equal to n right shift of 1? Because this is equivalent to writing n by 2 to the power 1 or n by 2. Remember, right shift operator. So I did the same thing. I just converted this into a bit stuff. Now, if you do bit operations, it is slightly faster than the other operations. That is why in most of the competitive programmers code, you'll find the odd check as this. This is their odd check. They will never write n modulo 2 equal to 1. They'll always write something like this. If they're dividing, they'll always write n right shift of 1. Right? If they're dividing it by 2. In most of your binary search code, when you write something as low plus high by 2, this is what you write, right? Like this is what you write. But the faster version is low plus high and then right shift by 1. Because right shift by 1 means dividing by 2. So this is how you count the number of set bits. If you're using C++ STL, in the STL lecture I've already told you, there is an internal function built-in underscore pop count, and you can pass in the integer. This will tell you the number of set bits in a given number. So there's one more way in which we can count the number of set bits. Let's take the number 84. If I try to write this in binary, it will be 1010 Now if I ask you to write n minus 1, which is 83, it's binary. You know what it will be. You'll take the rightmost bit, turn it to 0, and the right bits will be turned to 1. Everything else stays as it is on the left. So 10100111. Now if I ask you to do an AND, what you'll get is 0 0 0 0 1 0 1. So what I was able to do was, I was able to turn off the rightmost bit. I was able to turn off the rightmost bit by simply doing n and n minus 1. So once I've done it, I'll get a number like this. Correct? Now if I ask you to write a minus 1 of this number, like a minus 1 of this number, let's write this number, that's 1010000. Now a minus 1 of this number will be 1 1 1 1, a 0 here, and the left one will be same. So again, what has happened is this rightmost bit, which is 1, has been replaced with 0, and everything on the right has been replaced with 1s. Again, if you do an AND, what will happen is you'll get 0 0 0 0 0 and then a 0 1. So what has happened is you've turned off the rightmost bit. You've turned off the rightmost bit. Perfect. Again, if I take this number, which is 1 0 0 0 0 0 0, and I do a minus 1, the number that I'll get is 0 1 1 1 1 1. Now if I do an AND, I'll get 0 0 0 0 0 0. So what has happened is, again the rightmost bit has been turned off. So can I follow a similar pattern? Maybe yes. So thereby I'll write counter equal to 0, and I'll be like, okay, while n is not equal to 0, and at every step what I'll do is n equal to n and n minus 1, and I'll do a counter plus plus. So what will happen is, if there's a number like 84 and there are 3 bits which are on. At the first step, the rightmost bit is turned off. At the second step, the second rightmost bit is turned off. And at the last step, this one will be turned off. So I'll keep on doing n and n minus 1. I'll keep turning off the rightmost bit. And at the end of the day, n will be 0. So count will be your number of set bits at the end of the day. Now, what will be the time complexity over here? The time complexity over here will be bgo of the number of set bits. At the worst possible scenario, this can be bgo of 31 for an integer, which is similar to the one that we did when we were dividing by 2. Because in that scenario as well, the worst possible case is logarithmic base 2n, which can go as bgo of 31 if your number is as big as 2 to the power 31, like the biggest number. Then that can also take a lot of time. But since most of the numbers will not have all of them all of the bits as 1, this is a better approach to count the number of set bits, which is taking bgo of number of set bits. So remember this one. So yeah, that's it for this particular video. I hope you've understood everything. And if that is the case, please do consider giving us a like. And if you're new to our channel, do consider subscribing to us as well. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye-bye. Take care.